Hello and welcome back, and this is the very last lecture of the class and it's called Functions and Daemons. What I'm going to do is I'm going to show you how we can use recursion to define functions, and then we're going to do some function definition in Haskell. You may remember at the beginning of the class we looked at some assembly code. And here's the assembly code. Assembly code is like very much down at the lowest level of the machine. So these are individual operations. If you're doing CS106, you'll know the tiny machine and the operations that you can do. Well, this is assembly language programming. It says load up the value of x, add x to it, and then add the value of y. Store the result of doing all of those additions in the location in the location y, and then halt. So what does this actually do? Well, x, it calculates 3 times x plus 1. So all of these symbols here, all of this writing is exactly equivalent to writing lambda x 3x plus 1. That's my function. Lambda x 3x plus 1 seems a lot more compact and a lot more of a reasonable way to write things down. Why can't I just write that down? If I've got a function in my head that I want to write down, why can't I just writing it down like that? Well, this forms the basis of functional programming languages like Lisp, ML, and the language Haskell. So when you write functions in Haskell, we saw in the previous videos a little bit of this. When you write a function in Haskell, all you have to do is to specify what needs to be returned for a given input. So here I've written a function called myNot. It has type, that's what these 2 colons mean. Now myNot has type Boolean to Boolean. So it takes in a Boolean and it returns a Boolean. And then I have to enumerate all possible cases. So if the input is true, I return false. If the input is false, I return true. So the function is complete. We've covered all the possible values we might encounter. And as I said, the first line gives the type of the functions. So I can write this in Haskell, and we'll see that in a minute. We need to cover all possible inputs, but if we've got lots of possible inputs, we can save ourselves some writing by using this underscore, which we also saw in the video with trying out the Haskell language. Basically, it matches with anything. So here is a function myAnd. Now the type is a bit more complicated, but basically it means it takes in a Boolean and then another Boolean, and it returns a Boolean as the result. We pass them in one at a time because that's the way that the lambda calculus works. So myAnd of true and true is true. That's a special case. In fact, that's the only combination of inputs which will result in true being the output. And myAnd of anything else returns false. What Haskell does is it pattern matches. It will match the patterns one at a time as it goes down the page, top to bottom. And because this one is more specific, if I call myAnd on true and true, it will return true. But if I call myAnd on any other arguments, it will return false. So in other words, if I call myAnd on true false, false true, or false false, all of those will return false. So this is a pattern which basically, after a while, you'll realize this is the pattern for basically saying it takes in 2 arguments and it returns a single Boolean. So that's what the type is here. So here's what the underscore does. It basically means any possible input. So as an exercise, think about how you would define the function myOr. Takes two inputs, but it ORs them together using the logical OR function. So OR of true and true is true, OR of true and false is true, OR of false and true is true, OR of false and false is false. So how would you write that in Haskell using a similar idea to this one? And I'll give you the answer in a bit. Okay, so now I'm going to move on to the idea of recursion. And the way that I like to think of recursion is by having an infinite line of lazy daemons. Each daemon here does a little bit of a calculation for you, but after they've done one calculation, they get tired and they fall asleep. So in other words, they might add two numbers for you. They can also remember calculations. So let's say I want these daemons to calculate the sum of some numbers for me. How could I do that? How could I get the daemons to calculate the factorial function for me, given that they'll only do one calculation? To compute the factorial of 5, I have to do 5 times 4 times 3 times 2 times 1. That's a lot of calculations, and these guys only do one. So here is how I can get them to do it. I do it using two rules. So this is the algorithm that each daemon in line has. And the first one is the simple rule. If I give you 0, you return 1. The reason for that is that the factorial of 0 is defined as being 1. If you remember, the factorial is the number of ways that you can, a number of permutations you can have of a set of items of size n. Well, if you've got 0 items in your set, there's only one permutation, that's the empty set, so the answer is 1. Similarly, if you've only got one item in your set, there's only one permutation, so the factorial of 1 is also 1. However, if I've got 2 in my list, well, I could have AB or BA, both ways round, so that's 2. If I've got 3 items, I've got quite a lot of possibilities. There's ABC, ACB, BCA, BAC, CBA and CAB. So there's 6 possibilities, and I'm not going to do it for 4 because there's 24 of them. The rule is, though, if I want you to calculate the factorial of a number n, say I want you to calculate for me the factorial of 42. That's a lot of calculations. Well, what you can do is you can say, well, what I know is that 42, the factorial of 42 is 42 times the factorial of 41. If I could get some poor loser to calculate the factorial of 41 for me, I can just multiply it by 42. So what the daemon does is it passes it one down the line. So if I go back to my daemons, if I give this guy, I say, hey you, let's call him Steve. Hey Steve, what's the factorial of 42? He says, well, I can only do one calculation. So I'll do 42 times the factorial of 41. So he asks the next daemon down the line, we'll call him Steve as well. He says, hey Steve, what's the factorial of 41? So Steve here says, well, I don't know what the factorial of 41 is, but I know it's 41 times the factorial of 40. So he asks the daemon one down the line, who's also called Steve, hey Steve, what's the factorial of 40? Then, and so on and so on. And you basically pass it all the way down the line until one of them, let's do a smaller number. Let's say we give this guy the factorial of 3 to do. So he asks this guy what the factorial of 2 is, and then he asks this Steve what the factorial of 1 is, and then he asks this Steve, hey, what's the factorial of 0? Well, at this point, this Steve says the factorial of 0 is 1 and passes it back here to this Steve. So this daemon now says, okay, so the factorial of 1 is 1 times 1 and passes it back to this daemon. And this daemon then says, okay, so the factorial of 2 is 2 times 1, so that's 2, and passes it back to the daemon at the top Steve. And this Steve says, okay, so the factorial of 3 is 3 times 2, so that's 6. So this Steve then returns that value to me. And that's how they do it. So that's how this works. If we want to actually write that in Haskell, we would write it like this. We would say factorial is a function from integers to integers. The factorial of 0, that's 1. But the factorial of n is n times the factorial of n minus 1. So then it will calculate what the factorial of n minus 1 is, and it will keep recursing until it gets down to this row, this rule here. And this is recursive because it calls itself. Recursive code is code which calls itself. Let's have another recursive function. In Haskell, lists are used to, as you've seen, to hold an arbitrary number of objects of the same type. How can we get our daemons to calculate the length of a list? Well, we can write our rules like this. Hey daemons, here's your algorithm. If I give you the empty list, you'll return 0. Okay, let's say. But if I give you a non-empty list, just take the first element, throw it away, and then pass the daemon one down the line, next Steve, pass next Steve the list with that element remove first, and then say, okay, what's the length of that list next down the line, Steve? And then when next down the line Steve comes back with the answer, you then add 1 to it. So in other words, let's go back to our daemons and remember our list here. 23, 5, minus 17 and 6. So we pass the list length 4 to this guy. He takes the first one off and passes it to this guy. So there's now a list of length 3 here, then a list of length 2, then a list of length 1 to this guy, and he then passes the empty list to this chap here, who then says, that's 0. So in other words, the empty list has length 0. So 0 gets passed back from this guy to him. He adds 1 to it. So that's 1. He adds 1 to that, 2. He adds 1 to that, 3. He adds 1 to it, 4. And that's what then gets returned. So in Haskell, it will look like this. The length function, well, it's slightly trickier. It's a list of items, and the items are of any type. That's meant to be an alpha. That is an alpha. That's how we write alpha in Haskell. So the length function is from a list of items of any type, and it will return an integer. The length of the empty list is 0, or the length of a list, and we're doing pattern matching here, with an item at the front and a rest on the back. So we're matching that against our list. That is equal to 1 plus the length of the rest of the list. So in other words, what we're doing is we're taking a list here of length n, and this is a list of length n minus 1. So we're subtracting 1 from it each time, and eventually we'll get down to the empty list. And it's recursive. We see the same call on both sides. Let's see a calling diagram for this. A calling diagram is basically how you work out how it works. So len of 1, 2, 3, 4, well, that's going to be this version. So length of an item and a rest is 1 plus the length of the rest. So 1 plus the length of the rest. Then we have to calculate this. Again, it says a length of an item and a rest is 1 plus the length of the rest. So now we've got 1 plus the length of 3, 4. The length, this length, len of 3, 4, well again, it's the length of an item and a rest is 1 plus the length of the rest. Then we've got length of 4. Length of an item and a rest, now here the rest is the empty list. Remember that 4, the list 4, is the item 4 joined onto the empty list. We did that in our tutorial. So its length of 4 is 1 plus the length of the empty list. So finally we end up with 1 plus 1 plus 1 plus 1 plus 0 for the length of the empty list, and then we evaluate that to give 4. So having done all that, here's a little assignment for you to think about. Which of the following pieces of code are recursive? I've told you what recursion means, and that's what I want you to get out of this. I don't want you to be an expert Haskell programmer. We'll in fact teach you how to do that in 2nd year and in 3rd year. But I would like you to be able to at least spot recursion when it occurs. So the first 4 of these are Haskell type things. My not of true is false, recursive or not. My NAND of V1 and V2 is my not of my AND of V1 and V2. So I'm combining my not and my AND functions to make a NAND function. Recursive or not. Factorial of n is n times the factorial of n minus 1. Recursive, not recursive. My length of a first const onto a rest is 1 plus my length of the rest. Recursive or not. And then finally, I've got a bit of Java in here. If you're not doing Java, don't worry too much about this. It's just a loop. For integer, I is 0. I is less than n, I plus plus. So we start with I as having the value 0. We test for I being less than the value n, which is defined somewhere else. And then we add 1 to I each time around the loop. And then we're going to system out print line I. So that's just going to print out the value of I on the screen from 0 upwards. So this will print out the values I until we get to the value of I that's 1 less than n. Is that or is that not recursive? Then finally, we're going to look at a Haskell function called SumList. SumList of the empty list is 0. SumList of an item and a rest, item const onto a rest, is equal to the item plus the function SumList called on the rest. Okay, so hopefully you can see what this is going to do. So first of all, think to yourself, what does SumList 1, 2, 3 return? You should be able, through the lecture and through the Haskell tutorial that we did, you should be able to work out what that's going to return. And then, having done that, think about what in general does this function do? What's it? I'm going to pass it what, and what will it return? What's the input? What's the output? Why do we say that this function is recursive? So this function is recursive. Why is it? Then I'd like you to write out a calling diagram for SumList 1, 3, 5, 9. So in other words, do a similar job to the one that we did there for length. Do that on SumList. And then finally, with all of the information that you've got in this lecture, tell me what the type of that function is. So in the live sessions this week, we'll be looking at some Haskell programs. So hopefully it's been useful and interesting, and I'll see you in the Zoom sessions. Bye for now.